What if everything we know about speed is just the beginning? What if particles exist that don't just approach the speed of light, but blow right past it, leaving Einstein's cosmic speed limit in the dust? Picture this: tiny, unimaginably fast messengers zipping through the fabric of space-time, defying the laws of physics as we know them. These aren't just science fiction fantasies. They're a real, tantalizing possibility that physicists call tachyons. And if they're out there, they could rewrite the rules of reality itself. Think of tachyons as the universe's ultimate speedsters, particles born already moving faster than light, never slowing down, never obeying the same limits that bind the rest of existence. Imagine a race car that doesn't accelerate from 0 to 60, but starts at 1,000,000 miles per hour and only goes faster. That's the mind-bending nature of these hypothetical wonders. But here's the real kicker. If tachyons exist, they might hold the keys to technologies straight out of our wildest dreams: instant communication across galaxies, warp drives bending space-time, even glimpses into the future. The implications are so staggering, they blur the line between physics and magic. Yet the most thrilling part isn't just what tachyons could do, it's what their existence would mean for our understanding of the cosmos. For over a century, we've lived by Einstein's rules, where light speed is the ultimate barrier. But tachyons whisper a provocative question: what if that barrier isn't a wall but a doorway? A gateway to realms of physics we've barely dared to imagine. Today, we're diving headfirst into this electrifying mystery, exploring how these phantom particles could reshape everything from time travel to quantum computing, and why their discovery might be closer than you think. Buckle up, because we're about to take a ride to the edges of known science and beyond. To understand why tachyons turn physics upside down, we first need to grasp how they differ from every other particle in existence. Ordinary matter, everything from atoms to planets, falls into a category called tachyons. These are the slowpokes of the universe, always traveling below light speed. Then there are luxons, like photons, which hit light speed but never exceed it. Tachyons laugh at both groups. By definition, they're particles that don't just break the cosmic speed limit. They were never bound by it in the first place. Unlike tachyons that need infinite energy to approach light speed, tachyons would require infinite energy to slow down to it. They're born racing, like a cheetah that popped into existence already sprinting. Here's where things get weird. According to Einstein's equations, anything with real mass can't reach light speed because its mass would balloon toward infinity. But tachyons sidestep this entirely by having what's called imaginary mass, a mathematical quirk that makes their energy behave in reverse. The faster they go, the less energy they have. It's as if pressing a car's accelerator made it decelerate instead. This bizarre property isn't just a loophole, it's a full-scale assault on relativity's foundation. Einstein's theory carefully stitches space and time into a unified fabric where cause always precedes effect. Tachyons, though, could blur those lines, potentially allowing effects to happen before their causes, a notion that throws causality itself into chaos. Yet the real shock isn't just their speed, it's how they warp our understanding of reality. If tachyons exist, they'd be forever out of sync with our world, detectable only through their footprints. Imagine trying to photograph a bullet mid-flight with a camera that only captures slow-motion ripples. That's the challenge physicists face. These particles wouldn't leave traditional trails in detectors. Instead, they might manifest as sudden energy spikes or distortions in quantum fields, ghostly signatures hinting at a realm where time could flow backward and distances collapse to zero. It's a reminder that the universe might still hold layers of physics we've scarcely begun to peel back. The story of tachyons begins not with a groundbreaking experiment or a flash of observational insight, but with a bold theoretical leap in the swinging 60s. It was 1967 when physicist Gerald Feinberg published a paper that gave these faster-than-light particles their name, tachyon. derived from the Greek word tachys, meaning swift. But Feinberg wasn't just pulling the idea from thin air. The seeds had been quietly sprouting in the shadows of quantum mechanics for decades. Rewind to the early 20th century, and you'll find hints of this radical concept lurking in the equations of pioneers like Werner Heisenberg and Paul Dirac. Quantum theory had already shattered classical notions of certainty, introducing probabilities and uncertainties at the subatomic level. Yet the idea of particles breaking light speed remained taboo, a boundary even quantum weirdness seemed hesitant to cross. That is, until Feinberg dared to ask, what if relativity's speed limit wasn't universal? What if certain particles had been cheating the cosmic rulebook all along? His proposal sent ripples through the physics community. Some embraced it as a thrilling expansion of known physics, while others met it with fierce skepticism. Enter Richard Feynman, the charismatic Nobel laureate known for his razor-sharp intuition. He dismissed tachyons as mathematical curiosities, artifacts of equations rather than real phenomena. To Feynman, the universe had no room for particles that flouted causality, even on paper. The debate split physicists into camps, those who saw tachyons as a doorway to new physics and those who viewed them as mathematical ghosts. Meanwhile, science fiction writers seized on the idea with glee. By the 1970s, tachyons became a staple of futuristic storytelling, plot devices for time travel, instant communication, and alien technologies. Shows like Star Trek and novels by authors like Arthur C. Clarke wove them into their lore, blurring the line between speculative fiction and cutting-edge theory. Suddenly, tachyons weren't just equations in a journal. They were cultural icons, symbols of humanity's hunger to break free from physical limits. Yet beneath the pop culture frenzy, serious research trudged forward. Experiments sprung up to hunt for tachyon footprints, anomalies in cosmic ray data, unexpected energy spikes in particle colliders. So far, no smoking gun. But the very fact that physicists keep looking tells you something profound. Science thrives on the edges of the impossible. Whether tachyons are real or not, their legacy is undeniable. They've forced us to question the absolutes of physics, reminding us that every law might just be a temporary fence waiting for the right idea to leap over it. Einstein's theory of relativity is like the universe's rulebook, a set of laws so fundamental they've shaped our understanding of reality for over a century. At its heart lies one non-negotiable principle: nothing with mass can reach or exceed the speed of light. The math is clear: as an object accelerates, its mass balloons toward infinity, demanding infinite energy to push it further. It's the ultimate cosmic speed trap, and for Tardians, the ordinary particles we're made of, it's an unbreakable barrier. Enter tachyons, the hypothetical rogue agents that don't just ignore this rule, they flip it on its head. The key to this defiance lies in the Lorentz factor, the mathematical backbone of relativity. For ordinary particles approaching light speed, this factor predicts their mass and energy skyrocketing to impossible levels. But tachyons perform a clever mathematical sleight of hand. By possessing what physicists call imaginary mass, a concept rooted in the square root of -1, they invert the equation. Instead of requiring infinite energy to reach light speed, they'd need infinite energy to slow down to it. Picture a swimmer who can't stop moving forward, not because they're strong, but because the water itself refuses to let them break. This inversion births mind-bending paradoxes. Take causality, the idea that causes must always precede effects. If tachyons exist, they could theoretically send signals backward in time, creating situations where an event's consequence arrives before its trigger. Imagine a bullet hitting its target before the gun is fired, or a message from the future altering the past. These aren't just sci-fi tropes. They're legitimate nightmares for physicists who've built careers on relativity's rock-solid foundation. Yet the controversy doesn't stop there. Some theorists argue tachyons could be the universe's way of patching its own cracks, particles that exist outside our perceptual framework, like shadows cast from a higher dimension. Others dismiss them as mathematical phantoms, artifacts of equations taken too far. The debate rages because the stakes are cosmic. If tachyons are real, relativity isn't wrong but incomplete, a breathtaking reminder that even our most cherished theories might just be stepping stones to deeper truths. So why hasn't this debate been settled? For all their theoretical intrigue, tachyons remain elusive. No experiment has definitively caught one, though not for lack of trying. Detecting them would mean spotting particles that don't interact with matter the way electrons or protons do, particles that might only reveal themselves through gravitational ripples or quantum anomalies. It's like searching for a whisper in a hurricane, yet the hunt continues. Because here's the thing about science, sometimes the most revolutionary ideas are the ones that force us to question not just what we know, but how we know it. Imaginary mass sounds like something straight out of a wizard's spellbook, a property so strange it seems to defy logic. But in the world of tachyons, it's not magic, it's mathematics. Think of it like this: ordinary mass is like a bag of sand sitting on a scale, pulling downward with familiar weight. Imaginary mass, though, would be like that same bag suddenly pushing upward, as if gravity had flipped its rules. It's not that the sand vanishes or becomes unreal, it's just behaving in a way that turns our everyday expectations inside out. To grasp how this works, picture a rubber band stretched between two fingers. For normal particles, adding energy is like pulling the band tighter. It resists storing that energy as increased mass, but tachyons, they're the cosmic equivalent of a rubber band that snaps loose when you tug it. The more energy you pour into them, the less they behave like massive objects. Instead of fighting acceleration, they embrace it, diving deeper into faster-than-light territory with every nudge. This bizarre trait comes straight from the math of quantum field theory, where imaginary numbers, those built around the square root of -1, aren't just abstract symbols. They're tools that describe real, if mind-bending, possibilities. Here's the crucial twist: imaginary doesn't mean made up. In physics, it's a technical term for a specific kind of relationship between energy, mass, and motion. Tachyons with imaginary mass would still interact with the universe. They'd just do it on terms that look nonsensical to our Tardian-bound perspective. Imagine a car where pressing the gas pedal made it go backward. That's the kind of inverted logic we're dealing with. The real genius of this idea lies in how it sidesteps relativity's roadblocks. Einstein's equations don't explicitly forbid faster-than-light particles. They just demand that such particles couldn't slow down to light speed. It's like a cosmic game of limbo where the bar is set at light speed. Ordinary matter can't go under it, but tachyons start already beneath it, dancing in a realm where the rules are rewritten. Quantum field theory accommodates this by treating tachyons as excitations in a field with unusual properties, like ripples on a pond that travel faster than the water itself can move. So why hasn't imaginary mass shattered physics? Because the math allows for possibilities that nature might still reject. Just as equations once predicted antimatter before we found it, tachyons remain a thrilling what-if at the edge of theory. They're less about breaking the universe's rules and more about revealing hidden chapters in its playbook, ones where the familiar arrows of time and causality might not point the way we expect. Whether they're out there or not, the very fact that physics entertains such ideas proves how endlessly inventive and humbling the cosmos can be. Quantum field theory paints the universe as a bubbling sea of invisible fields, each humming with potential, waiting to spark into particles we can detect. Tachyons slide into this framework like a puzzle piece that doesn't quite fit yet might complete the picture in ways we never anticipated. At first glance, they seem like misfits, particles that refuse to play by the usual energy rules. But dig deeper and you'll find they're not breaking physics, they're revealing hidden layers of it. Take tachyon condensation, a phenomenon that sounds like science fiction but sits squarely in theoretical physics. Imagine a field like the Higgs field that gives particles mass, but in an unstable, high-energy state, like a pencil balanced on its tip. The slightest nudge sends it tumbling into stability, releasing energy as it falls. Now replace that pencil with a tachyon field. Here's the twist: instead of settling into a familiar low-energy state, it condenses into a configuration that breaks symmetries, reshaping the very fabric of reality around it. This isn't just theoretical poetry. It's how some physicists believe the Higgs boson itself might have emerged in the early universe, a tachyon-like field freezing into the structure that now gives mass to everything. Visualizing this is like watching water freeze in reverse. Normally, cooling water turns it to ice, locking molecules into place. But tachyon condensation would be like superheating ice until it suddenly reorganizes into something entirely new, rewriting its own rules mid-process. This phase transition isn't just a curiosity, it's a cosmic sculptor, carving out the laws of physics from a hotter, denser past. If tachyons exist, they might not just be particles. They could be the universe's way of transitioning between different sets of physical laws, like a snake shedding its skin to reveal new possibilities underneath. Yet the implications stretch even further. In string theory, tachyons pop up as artifacts of unstable configurations, hinting at deeper, more fundamental theories waiting to be uncovered. Some researchers argue these phantom particles could signal where our current math fails, like cracks in a dam pointing to the pressure building behind it. Others see them as placeholders for physics we haven't yet invented, mathematical breadcrumbs leading to a grander theory. The beauty of quantum field theory is how it accommodates such wild ideas without flinching. It treats tachyons not as mistakes, but as messengers telling us where the map of reality ends and the uncharted territory begins. Whether they're real or not, their presence in our equations forces us to ask, are we seeing glitches in the matrix or the first hints of a universe far stranger than we ever dared to dream? If time is an arrow flying relentlessly forward, tachyons might be the feathers that make it wobble or even reverse course. The idea that these particles could move backward in time isn't just wild speculation. It emerges from the bedrock of modern physics itself. Take Feynman diagrams, those elegant scribbles physicists used to map particle interactions. Normally, they show particles marching forward along the time axis. But flip the script, and suddenly an antiparticle moving forward in time looks identical to its ordinary counterpart moving backward, like rewinding a film reel of an electron's life. Now replace that electron with a tachyon, and the equations suggest something even stranger. A particle that doesn't just rewind but exists outside time's usual flow altogether. This isn't just abstract math. CPT symmetry, the holy trinity of charge conjugation, parity, and time reversal, demands that the universe treats matter and antimatter, left and right, past and future as fundamentally balanced. Tachyons, with their imaginary mass, could be the loophole that exploits this symmetry, threading the needle between cause and effect. Picture a tachyon signal zipping from Earth to Alpha Centauri faster than light. From our perspective, it arrives before it's sent. For an alien watching from Alpha Centauri, the same event might look like Earth's message is echoing from their future. The result, a cosmic game of telephone where the sequence of events depends entirely on who's holding the stopwatch. Of course, this opens the mother of all paradoxes. What if you used tachyons to, say, send a message to your past self warning not to send the message? Or worse, to prevent your own birth? The grandfather paradox isn't just a thought experiment here. It's a glaring red flag that tachyons might unravel causality itself. Some physicists argue nature would simply forbid such nonsense through mechanisms we don't yet understand, like quantum probabilities conspiring to erase contradictions before they happen. Others propose a multiverse workaround. Every tachyon-fueled time loop spawns a new branch of reality, so your past-altering message just creates a divergent timeline where your grandfather lives, leaving your original history untouched. Yet the wildest twist isn't whether tachyons can mess with time, it's whether they already do. Quantum mechanics teams with spooky action at a distance, where particles influence each other instantly across vast distances. Could tachyons be the hidden couriers behind these effects, knitting the universe together with threads that stretch backward through time? It's a dizzying thought, but one that hints at a cosmos far stranger and far more interconnected than we ever imagined. Whether tachyons are time-traveling troublemakers or just mathematical mirages, their very possibility forces us to confront a profound truth. Time itself might not be the rigid scaffold we think it is, but a fluid, mutable thing waiting for the right particle to bend it. Tachyons don't just bend the rules of speed, they twist the very fabric of time into knots. Imagine a particle so fast it outruns cause and effect, arriving at its destination before it even leaves. This isn't just theoretical sleight of hand. It's a direct consequence of relativity's equations when applied to faster-than-light objects. If tachyons exist, they could serve as nature's own time machines, stitching together moments in history like a needle threading through the folds of space-time. But how picture a tachyon message sent from Earth to a distant star? For an observer on that star, the signal might appear to arrive before it was emitted, an effect that turns chronology into putty, malleable, and strange. Now pair this with wormholes, those hypothetical cosmic shortcuts where space-time folds like a piece of paper connecting two distant points. In theory, a tachyon-fed wormhole could become a time tunnel, with particles zipping through not just across space, but backward through years or even centuries. The catch: wormholes, if they exist at all, are notoriously unstable, prone to collapsing before anything could traverse them. Enter tachyons. Their exotic energy properties might theoretically stabilize these fragile structures, acting like cosmic scaffolding to hold the wormhole open long enough for, well, who knows what. The possibilities spiral from there, limited only by the imagination and the harsh constraints of physics as we understand it. Then there's the Alcubierre drive, a concept ripped straight from science fiction but grounded in real math. Proposed by physicist Miguel Alcubierre in 1994, this theoretical engine would warp space-time itself, compressing the fabric of the universe in front of a spacecraft while expanding it behind, effectively creating a bubble of motion without breaking light speed locally. But here's where tachyons sneak in. Some models suggest that sustaining such a warp bubble might require matter with negative energy, a property tachyons could hypothetically provide thanks to their inverted energy dynamics. It's like trying to inflate a balloon by sucking air out of it, counterintuitive but not impossible under the right conditions. Pop culture loves this stuff for a reason. Star Trek famously used tachyons as plot devices, detecting cloaked ships, powering time jumps, even fixing fractured timelines. While Hollywood takes liberties, the underlying fascination taps into a real human craving, the dream of breaking free from time's iron grip. Whether it's Doctor Who's TARDIS or Interstellar's Tesseract, the appeal is universal. We're hardwired to wonder, what if? Yet for all the tantalizing maybes, it's crucial to remember these ideas remain untested hypotheses, speculative leaps at the edge of known physics. No wormholes have been observed, no Alcubierre drives built, no tachyons conclusively detected. But that's the beauty of theoretical physics. It plants flags in the unknown, giving us targets to chase. Even if tachyons never materialize, the questions they raise about time, causality, and the universe's hidden architecture are too electrifying to ignore. After all, every revolutionary discovery began as someone's wild thought experiment. Who's to say the next won't emerge from the shimmering haze of a tachyon's trail? Imagine holding a phone that doesn't just connect you across continents, it dials straight into the past. This isn't the plot of a time travel movie, it's the tachyon-based antitelephone, a thought experiment that turns casual chit-chat into a causality crisis. Here's how it works. If tachyons exist, their faster-than-light speed could let you send a message that arrives before you've even sent it. Picture this. You record a tachyon transmission saying, "Don't watch this video," then fire it off to yourself 1 hour ago. The you from the past gets the warning, heeds it, and never records the message in the first place. But if the message was never sent, how did your past self receive it? This dizzying loop is more than just a brain teaser. It exposes the razor's edge physics walks when faster-than-light communication enters the picture. Einstein's relativity stitches cause and effect into an unbreakable sequence, first the lightning, then the thunder. Tachyons threaten to unravel that sequence by allowing effects to precede causes, like thunder rumbling before the storm forms. The antitelephone scenario isn't just about breaking time's rules. It reveals how deeply interconnected causality is with our experience of reality. Without it, the universe becomes a hall of mirrors where actions have no anchor and history rewrites itself endlessly. Physicists call this a closed time-like curve, a path through space-time that circles back on itself, creating a feedback loop where the future influences the past. Some theories suggest nature might prevent such paradoxes through quantum mechanics, where probabilities conspire to block contradictions before they happen. Others propose a multiverse escape hatch. Every tachyon message spawns a new timeline, so your warning creates a parallel universe where you skip the video, while your original self carries on obliviously. The antitelephone's true power lies in what it teaches us. Even if tachyons never exist, the paradox forces us to question whether time's arrow is as immutable as it feels, or if it's just one thread in a far stranger cosmic tapestry. After all, quantum entanglement already shows particles influencing each other instantly across vast distances. Could nature already be playing by tachyonic rules we just don't fully grasp? Until we know for sure, the antitelephone remains both a cautionary tale and an invitation to peer beyond relativity's horizon, where time might not flow in just one direction after all. Particle accelerators like Fermilab and CERN have spent decades smashing matter together at nearly light speed, hunting for physics beyond the standard model, including tachyons. These colossal machines are perfect tachyon traps in theory, capable of creating conditions where exotic particles might flicker into existence. Take Fermilab's Tevatron, which once ruled as the world's most powerful collider before the Large Hadron Collider. In the 1980s and 90s, physicists meticulously combed through its debris, searching for anomalies, unexplained energy spikes, or missing momentum that could hint at faster-than-light particles slipping through their detectors like ghosts. The result, silence, not a single confirmed tachyon signature, but null results aren't failures, they're clues. The challenge isn't just finding tachyons, it's recognizing them at all. Ordinary particles leave clear fingerprints, ionized trails in cloud chambers, flashes of light in scintillators, or predictable energy deposits in calorimeters. Tachyons, though, dance to a different tune. If they exist, they'd likely zip through detectors without interacting electromagnetically, leaving no conventional trace. Imagine trying to catch a bullet with a net made of smoke. You might only spot them indirectly through gaps in collision energy budgets, or as missing momentum that can't be accounted for by known particles. Even then, the signal could drown in background noise or be mistaken for detector glitches. That's why CERN upcoming upgrades are so tantalizing. The high-luminosity LHC, set to ramp up in the late 2020s, will smash protons together at unprecedented rates, generating billions of collisions per second. More collisions mean more chances for rare events, including potential tachyon births. New detectors with sharper resolution could catch subtler anomalies, while advanced algorithms might sift through data for patterns too faint for human eyes. Some theorists even speculate that tachyons, if they're tied to dark matter or extra dimensions, might reveal themselves through gravitational ripples or distortions in quantum fields, signatures today's instruments are only beginning to probe. The irony, tachyons might be hiding in plain sight, masked by our own assumptions. Every time a collision's energy doesn't quite add up or a particle decays slightly too fast, there's a whisper of possibility. Until we build tools sensitive enough to listen, these cosmic speedsters could keep outrunning detection, leaving us chasing shadows at the edge of physics' known frontier. While particle colliders hunt for tachyons on Earth, the universe itself might be teeming with these elusive speedsters hiding in plain sight across the cosmos. Astrophysicists have turned their telescopes skyward, probing the darkest corners of space for clues that tachyons could solve some of the universe's most stubborn mysteries. Take dark energy, the enigmatic force accelerating the expansion of the universe. Scientists know it exists because galaxies are fleeing from each other faster than gravity alone can explain. But what if tachyons are the invisible puppeteers behind this cosmic runaway? If these particles permeate space, their peculiar energy properties could act like anti-gravity, pushing the universe apart at ever-increasing speeds. Then there's the puzzle of ultra-high-energy cosmic rays particles bombarding Earth with energies so extreme, they defy conventional explanations. Some of these rays pack more punch than a major league fastball, yet their origins remain shrouded in mystery. Could tachyons be the culprits? Theories suggest that if these particles exist, they might decay into ordinary matter under certain conditions, releasing bursts of energy so violent they dwarf anything our particle accelerators can produce. It's like finding footprints of a creature that moves too fast to be seen. The damage is visible, but the cause remains just out of view. Neutrinos, those ghostly particles that barely interact with matter, add another layer of intrigue. Experiments like IceCube have detected neutrinos with energies that don't quite fit the standard model's tiny deviations that could be statistical noise or whispers of tachyonic influence. If neutrinos occasionally borrow properties from faster-than-light particles, even momentarily, it might explain why some arrive with unexpected energies or timings. Imagine a marathon runner who somehow teleports mid-race, crossing the finish line a fraction of a second before the clock says they should. That's the kind of anomaly physicists are scrutinizing for hints of tachyon involvement. Gamma-ray bursts, the universe's most violent explosions, also offer tantalizing hunting grounds. These celestial fireworks can outshine entire galaxies for brief moments, and their light curves sometimes show peculiar features like flickers or delays that current models struggle to explain. Tachyons, with their ability to potentially outrun light itself, might leave faint imprints in these bursts like shadows cast by unseen runners in a cosmic relay race. Yet the most compelling evidence might not come from any single observation, but from the gaps between them, the anomalies that refuse to fit neatly into our existing frameworks. Whether tachyons are real or not, the search for them has already reshaped how we interrogate the universe's deepest secrets. Every unexplained energy spike, every cosmic ray with too much punch, and every neutrino that arrives a little too soon is a breadcrumb on the trail. One that could lead us to rewrite the laws of physics or just maybe catch a glimpse of particles that play by entirely different rules. Dark matter is the universe's most frustrating jigsaw puzzle. We know it's there because galaxies spin faster than their visible mass should allow, because light bends around invisible gravitational anchors, because the cosmos behaves as if it's stuffed with unseen matter. Yet after decades of searching, we've caught precisely zero of whatever's causing it. Enter tachyons. What if the answer isn't just hidden matter, but matter moving faster than light? At first glance, tachyons seem like bizarre candidates for dark matter. They're hypothetical particles defined by speed, not stealth, more cosmic sprinters than shadowy phantoms. But dig deeper and the fit gets intriguing. Like dark matter, tachyons wouldn't interact electromagnetically, making them invisible to traditional telescopes. Their bizarre energy properties could explain dark matter's gravitational grip without clumping like ordinary matter. potentially solving the cuspy halo problem where simulations predict dense dark matter cores that observations don't support. Imagine a swarm of tachyons buzzing through galaxies at superluminal speeds too fast to settle into dense clusters, yet collectively massive enough to bend space-time with their gravity. Compare this to the usual suspects. WIMP weakly interacting massive particles have been the reigning dark matter champions for years, theorized to lumber through space like celestial glaciers, their sheer numbers accounting for missing mass. Actions, another favorite, are ultra-lightweight particles that behave more like a pervasive quantum fog. Tachyons offer a radical alternative, dark matter not as sluggish or diffuse, but as something fundamentally unbound by the speed constraints shaping normal matter. It's the difference between searching for a missing person and realizing they were never lost, just moving too fast to track. The math even hints at a tantalizing symmetry. If ordinary matter Tachyons obeys E equals mc2 and light Luxons follows E equals pc, tachyons complete the set with their own energy-momentum relationship, one that could, in theory, balance the universe's books in ways we haven't yet imagined. Some models suggest tachyonic dark matter might naturally emerge from higher dimensional theories or exotic vacuum states, weaving itself into the fabric of space-time without needing separate particles at all. Of course, the lack of empirical evidence is glaring. No experiment has spotted tachyons, let alone confirmed them as dark matter. Critics argue they're too slippery, even for dark matter's elusive standards. How do you weigh something that might have imaginary mass? But here's where creativity thrives. Papers from theorists like Nobel laureate Frank Wilczek have explored how tachyon-like fields could condense into stable, energy-releasing configurations, effectively freezing into dark matter analogs. Others propose hybrid models where tachyons interact with conventional dark matter, creating dynamic feedback loops that explain galactic rotation curves without over-relying on any one particle type. The real value of tachyon dark matter isn't just in its plausibility, it's in how it stretches our thinking. Physics progresses not just by finding answers, but by asking better questions. Whether tachyons explain dark matter or not, they force us to consider that the missing mass of the universe might not be hiding in the shadows, but racing through them, forever one step ahead of our detection. And in a cosmos where 95% of everything remains unknown, that kind of thinking isn't just useful, it's essential. String theory has long been the playground for physicists chasing the universe's deepest secrets, a realm where particles are replaced by vibrating strings and extra dimensions curl into invisibility. But buried in its elegant equations lies an uninvited guest, the tachyon. Unlike other theories that treat tachyons as unwelcome anomalies, string theory gives them a starring role, not as particles, but as alarm bells ringing in the mathematical foundations of reality. These tachyons aren't just breaking speed limits, they're flashing warning signs that certain configurations of strings are fundamentally unstable, teetering on the edge of collapse like a tower of cards in a breeze. The key to understanding this lies in tachyon condensation, a process that sounds like something from a high-energy fairy tale but is deadly serious physics. Picture a field like the Higgs field, but instead of settling into a calm, low-energy state, it's trapped in a precarious high-energy perch. The tachyon here isn't a particle zipping around. It's the field's way of screaming, "This setup won't last." As the field decays or condenses, it releases energy, shedding its unstable state like a snake shedding skin, and in doing so, it can rewrite the very rules of physics in its vicinity. This isn't just theoretical noodling. It's how some physicists believe the early universe might have transitioned between different phases of existence, each condensation event carving out new laws from the chaos. Brain-world scenarios, string theory's bold proposition that our universe is a three-dimensional brain floating in a higher dimensional bulk, add another layer of intrigue. In these models, tachyons can arise when brains collide or decay, like cosmic fault lines slipping under pressure. Imagine two sheets of paper, the brains drifting toward each other in a vast, unseen space, the bulk. As they near collision, tachyon fields erupt, marking the instability before the brains either annihilate or rebound, potentially birthing new universes in the aftermath. It's a dramatic reshuffling of reality's deck, with tachyons as the telltale shimmer of impending change. What makes string theory's take on tachyons so fascinating is how it reframes their role. They're no longer just hypothetical particles straining against relativity's limits. They're transformative agents, catalysts for cosmic evolution. When a tachyon field condenses, it doesn't just vanish, it can spawn entirely new physics, like a dying star seeding space with the elements for planets. Some theorists even speculate that the Higgs mechanism itself, which gives particles mass, might be the aftermath of an ancient tachyon condensation event, a frozen echo of the universe's turbulent youth. Yet the most radical idea is that tachyons might not be problems to solve, but clues to a grander symmetry. If string theory's landscape of possible universes is real, then tachyon condensations could be the bridges between them, doorways to regions where gravity behaves differently, or time flows backward, or new forces emerge. It's a reminder that instability isn't always destructive. Sometimes it's the universe's way of innovating, of testing the boundaries of what's possible. And if tachyons are the scribbles in the margins of string theory's equations, they might just be the graffiti pointing us toward the next revolution in physics. If tachyons exist with their reality warping speed and inverted physics, why hasn't the universe already torn itself apart? This is the tachyon catastrophe, a paradox that keeps physicists awake at night. Think of it like filling a room with invisible dynamite. If tachyons are as unstable as theory suggests, their mere existence should trigger an unstoppable chain reaction, releasing infinite energy that vaporizes space-time itself. Yet here we are in a seemingly stable cosmos. So what's protecting reality from these hypothetical wrecking balls? One answer lies in decay pathways, the cosmic safety valves that might prevent tachyons from tipping the universe into chaos. Imagine a tachyon as a match struck in a room full of gunpowder. Normally, it'd ignite everything instantly, but if that match could somehow fizzle out before touching the powder, disaster is averted. That's the idea behind tachyon decay. These particles might spontaneously transform into safer, slower forms of energy before they can wreak havoc. Some models suggest they'd shed their excess speed by emitting photons or other particles, like a speeding car cooling its brakes by throwing off sparks. Others propose they'd annihilate upon contact with ordinary matter, leaving behind only a faint ripple in quantum fields. Then there's spontaneous symmetry breaking, a phenomenon as elegant as it is strange. Picture a pencil perfectly balanced on its tip. The slightest breeze sends it toppling, choosing a direction at random. In physics terms, that fall breaks the symmetry of the pencil's initial state. Now replace the pencil with a tachyon field. In its high energy state, the field is unstable like that pencil standing upright. But as it decays, it falls into a stable configuration, locking tachyons into a harmless phase where they can't trigger universal collapse. This isn't just speculation, it's how the Higgs field works, freezing into its current state moments after the Big Bang and giving particles mass in the process. Tachyons might follow a similar script, their destructive potential neutralized by the universe's own self-correcting mechanisms. Critics counter with a simpler explanation. Tachyons don't exist, and the catastrophe is just a mathematical red flag warning us that faster-than-light particles are impossible. But even if that's true, the paradox has value. Wrestling with the tachyon problem has led physicists to profound insights about vacuum decay, quantum stability, and the delicate balance that keeps our universe intact. It's a reminder that sometimes the most useful ideas aren't the ones that describe reality, but the ones that force us to defend it. Science fiction has teased us for decades with visions of instant communication across the stars. No lag, no waiting years for a reply from Alpha Centauri. Just real-time conversations spanning light years as easily as a phone call next door. From Star Trek's subspace channels to Ender's Game's iconic Ansible, these technologies share one thrilling premise: beating light at its own game. But here's the twist: while quantum entanglement often gets cast as the real-world Ansible, it's actually a cosmic letdown for faster-than-light messaging. Entangled particles do affect each other instantly, yes, but that connection can't carry information the way sci-fi promises. Measuring one particle collapses its state randomly, meaning you can't encode a message in those changes. It's like trying to send Morse code by shaking a pair of magic 8 balls and hoping the answers align. This is where tachyons swoop in as the universe's ultimate loophole. Unlike entangled particles, which obey quantum rules but stay light speed compliant, tachyons by definition live beyond that limit. Picture them as cosmic couriers, darting between stars with messages strapped to their backs, unshackled from the delays that plague radio waves or lasers. The moment you transmit a tachyon signal, it arrives at its destination before your finger leaves the button, at least, mathematically speaking. Ender's Game's Ansible might not be pure fantasy after all if these particles exist. It could simply be a tachyon transceiver encoding data in pulses that outrun time itself. But before we draft blueprints for galactic WhatsApp, there's a catch buried in the fine print. Even if tachyons exist, using them for communication resurrects all those causality headaches. The same time-travel paradoxes that make physicists wince. Send a tachyon message to a colony 10 light-years away, and depending on your relative motion, recipients might decode it 10 years before you sent it. Cue the grandfather paradox redux. What if that message warns them not to establish the colony in the first place? Suddenly, your signal becomes its own eraser, vanishing the very event that prompted it. The irony is delicious. The same property that makes tachyons perfect for instant messaging also threatens to turn the universe into a hall of mirrors, where cause and effect spiral into infinite loops. Some theories suggest nature might prevent this through quantum censorship, where probabilistic filters block paradoxical signals before they can disrupt reality. Others argue tachyons might simply be incapable of carrying coherent information, their signals devolving into noise the moment they breach light speed. Yet the dream persists because the stakes are so tantalizing. Imagine a future where spacecraft sync with Earth via tachyon networks, where astronomers watch supernovas unfold in real time across galaxies, or where humanity finally solves the loneliness of interstellar travel by stitching the cosmos together with threads of instantaneous connection. Whether tachyons can deliver that future remains unknown, but the fact that physics even entertains the possibility is a testament to how wildly inventive our universe might yet be. For now, the Ansible remains fiction, but the equations leave the door ajar just enough to keep us reaching for it. From Tony Stark's lab to the TARDIS control room, tachyons have become the go-to technobabble for sci-fi writers needing a dash of cutting-edge mystique. Marvel fans know them as the secret sauce in Iron Man's repulsor tech. Those glowing blue beams aren't just pretty visual effects. According to the comics, they're powered by tachyon pulses that defy conventional physics. Of course, real-world tachyons wouldn't just juice up armor, they'd rewrite causality itself. But that's the magic of pop culture. It takes a kernel of scientific speculation and runs wild. Cue the iconic Iron Man scene where Tony casually name-drops tachyons mid-battle, making them sound as mundane as Wi-Fi. Then there's Doctor Who, where the Doctor's time-traveling adventures lean hard into tachyon lore. The TARDIS doesn't just hop through time, it supposedly rides tachyon currents in the space-time vortex. One episode even featured a tachyon-powered time mirror that let characters glimpse alternate timelines. A clever nod to tachyon's real theoretical link to time loops, even if the execution leans more fairy tale than physics. The show's genius, it wraps complex concepts in whimsy, making tachyons feel like cosmic fairy dust. But for sheer conspiracy-laden drama, nothing beats The X-Files. Remember Season 6, Three of a Kind, where a tachyon beam becomes the key to undoing alien brainwashing. The script treats tachyons like a paranormal Swiss Army knife particle plot device. It's hilariously off base from actual science. Tachyon detectors don't double as truth serums, but that's the charm. These stories aren't aiming for textbook accuracy, they're tapping into the cultural electricity of an idea just plausible enough to thrill. What's fascinating isn't the inaccuracies, it's how consistently pop culture latches onto tachyons' most tantalizing trait, their ability to bend rules. Whether it's Star Trek's tachyon-based cloaking devices or Fringe's dimension-hopping tech, writers instinctively grasp that these particles represent the ultimate what if. They're not just faster than light, they're faster than imagination, letting storytellers shortcut through the usual constraints of physics with a single technobabble flourish. Yet buried beneath the Hollywood gloss is a sly tribute to real science. Every time a character shouts, "Fire the tachyon beam," they're channeling humanity's oldest urge to outrun limits to touch the impossible. And who knows, maybe one day, fiction's wildest tachyon tales will seem quaint compared to the truths we uncover. Until then, enjoy the ride, warp speed storytelling included. Tachyon-based technologies sound like they belong in the pages of a sci-fi novel, until you realize how close they might bring us to reshaping the future of human innovation. Picture a starship engine that doesn't just inch toward light speed but vaults past it effortlessly, powered by tachyon thrust. Unlike conventional rockets that guzzle fuel and fight against Einstein's speed limit, a tachyon drive would exploit these particles' innate faster-than-light nature, turning them into cosmic propellant. Imagine a vessel accelerating not by pushing against spacetime but surfing atop it, like a surfer catching a wave that never ends. The engineering hurdles are staggering, of course. Harnessing particles that might decay instantly or warp causality isn't exactly Starship Enterprise-level tech yet. But the math doesn't forbid it, and that's enough to keep physicists and engineers dreaming. Now shift gears to computing. Today's quantum computers manipulate qubits to perform calculations at speeds that dwarf classical machines, but even they hit walls imposed by light's finite pace. Tachyon computers, in theory, could blow past those limits. Instead of relying on electrons or photons bound by light speed, these machines might use tachyons to transmit information instantaneously across any distance. Think of it like upgrading from a dial-up modem to fiber optic, except the fiber stretches across galaxies without latency. A tachyon processor could solve problems in picoseconds that would stump today's supercomputers for millennia, from simulating entire universes to cracking encryption deemed unbreakable. Yet the most transformative application might be communication. Today's quantum networks promise unhackable encryption, but they're still stuck with light speed delays. Tachyon-based messaging could link Earth and Mars or even distant star systems, with zero lag, enabling real-time collaboration across interstellar distances. Colonies on Proxima Centauri wouldn't wait 4 years for Earth's replies. They'd chat like neighbors texting across the street. The catch: building a tachyon modem would require detecting and controlling particles we're not even sure exist, then engineering them to carry data without unraveling spacetime's fabric. It's like trying to weave a tapestry with threads that might vanish the moment you touch them. Compare this to today's cutting-edge tech. Quantum computing exploits entanglement and superposition, but it's still bound by locality and the speed of light. A quantum bit in Tokyo can't influence its entangled partner in New York faster than light can travel between them. Tachyon tech, by contrast, would treat light speed as a starting line, not a finished tape. The gap between current quantum experiments and tachyon possibilities is like comparing a steam engine to a warp drive. One obeys known physics while the other rewrites the rulebook entirely. For now, these ideas live in equations and thought experiments, but history's full of technologies that leapt from impossible to indispensable in a blink. The transistor, the laser, even the internet, all began as speculative theories before reshaping civilization. Tachyon tech might follow the same arc, or it might remain a beautiful mirage at physics' frontiers. Either way, the mere possibility pushes us to ask what's truly fundamental and what's just a temporary limit waiting to be shattered. The moment we unlock tachyon technology, we don't just break the speed barrier, we shatter the ethical framework that keeps reality predictable. Imagine a world where a message sent today could alter yesterday's decisions, where actions ripple backward with consequences no court of law could untangle. Films like Looper and Primer don't just entertain with time loops and hitmen targeting their past selves. They force us to confront the moral quicks and of tampering with cause and effect. What happens when a government weaponizes tachyons to erase political rivals before they rise to power, or when terrorists send warnings to their past selves to evade capture? The moment we crack open the door to time-altering tech, we invite chaos we might never contain. Consider the surveillance nightmare. Today's privacy debates pale next to a future where tachyon monitors could literally watch crimes before they occur. Predictive policing already skirts ethical lines, but what if authorities could intercept criminals mid-act by intervening in their past? The legal system would implode. How do you prosecute someone for a murder they haven't committed yet? The paradoxes spiral. If you arrest the would-be killer, their victim might never have existed to report the threat in the first place. It's justice turned inside out, where punishment precedes the crime and evidence evaporates with every intervention. Then there's the existential toll. Human psychology hinges on linear time, regret, redemption, and the weight of irreversible choices. Tachyons could erase that gravity, letting us undo mistakes with the ease of deleting a text. But without consequences, what shapes our morality? Primer's engineers unravel their lives not because their time machine fails, but because it works too well, leaving them stranded in recursive loops of suspicion and paranoia. The real danger isn't breaking physics, it's breaking the fragile narratives that make us human. Even benevolent uses tremble with unintended fallout. Medical tachyons might rewind cancer diagnosis to stage 0, but who gets access? A world where the wealthy can literally buy time while others suffer isn't sci-fi. It's an inevitability unless we grapple with these questions now. The irony is brutal. The same particles that could unite the cosmos might tear society apart along fault lines of power and privilege. Perhaps the sharpest lesson comes from fiction's cautionary tales. Looper's protagonist spends his life fleeing the consequences of his own paradoxes, only to realize control was always an illusion. Tachyons offer godlike power, but history's clearest pattern is this: every tool becomes a weapon, every breakthrough a Pandora's box. Before we chase the how, we'd better answer the should, because once causality cracks, there's no undo button for reality itself. The idea of parallel universes once felt like pure science fiction until quantum mechanics handed us the math to take it seriously. Enter Hugh Everett's many worlds interpretation, where every quantum decision spawns a new timeline, endlessly branching like a cosmic choose-your-own-adventure book. Now toss tachyons into this multiverse soup, and suddenly those branching paths might not be so separate after all. If these particles truly ignore the speed of light, could they slip between timelines like ghosts through walls, stitching alternate realities together? Picture this: a tachyon emitted in one universe doesn't just race through space, it vibrates at a frequency that resonates across the multiverse. Like a radio tuning into different stations, these particles might carry echoes of events from parallel worlds. In one universe, you skipped breakfast. In another, you invented cold fusion. Tachyons could be the static between those channels, leaking traces of what if into our reality. It's not quite Slider's portal hopping, but something subtler: a faint quantum bleed-through where probabilities whisper to each other across the void. This gets wilder when you consider quantum superposition. Before a particle state is measured, it exists in all possible states at once, Schrödinger's infamous cat, both dead and alive. Collapse that wave function and the universe chooses one outcome, while Everett's theory says the others play out in parallel. Now imagine a tachyon entangled across these splits. Its superluminal speed might let it remain aware of multiple outcomes simultaneously, acting as a bridge between timelines. A single tachyon could, in theory, be part of 2 or 2 billion different versions of history at once, like a cosmic diplomat with passports for every possible reality. Critics argue this veers into metaphysics, but the math doesn't flinch. Some string theory models suggest tachyons could arise from colliding brains, enormous membranes floating in higher dimensional space. When these brains smash together, the energy might birth not just one universe, but a cascade of them, with tachyon fields threading through the multiverse like stitches in a quilt. It's a far cry from hopping between worlds with a handheld device, but it hints at a deeper connectivity beneath the fabric of existence. The kicker. If tachyons link timelines, they might explain déjà vu or those eerie moments when reality glitches, like hearing a phone ring seconds before it actually does. Could these be stray tachyons, brief leaks from a universe where events unfolded slightly ahead of ours? Or worse, what if someone in a parallel world is already using tachyon tech to tweak our timeline, bending causality like a hacker manipulating code? Whether tachyons are multiverse messengers or just mathematical phantoms, they force us to confront a breathtaking idea. Reality might be thicker than we ever dreamed, layered with unseen dimensions and alternate histories, all just a tachyon's whisper away. The idea of tachyons often gets tangled in wild exaggerations. Some say they demolish Einstein's work, others dismiss them as pure fantasy, but the truth, it's far more nuanced. Let's cut through the noise with a reality check. First, the myth that tachyons disprove relativity misses the mark entirely. Einstein's equations don't explicitly forbid faster-than-light particles. They just demand that such particles could never slow down to light speed. Think of it like a highway where ordinary cars can't reach warp speed, but tachyons are vehicles born already in hyperdrive, never touching the speed limit. Physicists like Sean Carroll emphasize this distinction. Tachyons don't break relativity, they expose its unexplored edges. Then there's the pop culture baggage. Tachyons aren't sci-fi fairy dust, despite how often shows like Star Trek treat them as catch-all plot devices. Real theoretical work on tachyons dates back to serious papers by Gerald Feinberg and others, rooted in quantum field theory's rigorous math. The difference: sci-fi tachyons do whatever the script needs: power time machines, cloak spaceships, even reverse aging. Real tachyons, if they exist, would obey strict rules, like their energy decreasing as they accelerate, a quirk that makes them behave like cosmic unicycles where pedaling harder slows you down. Another common mix-up, assuming tachyons are just dark matter candidates in disguise. While their hypothetical properties, like not interacting with light, overlap with dark matter's mysteries, most physicists see them as separate puzzles. Dark matter's gravitational effects suggest it's slow-moving and abundant, while tachyons, by definition, would be speed demons, possibly too rare or unstable to account for the universe's missing mass. It's like confusing a stealth jet with a meteor, both hard to spot but fundamentally different beasts. The biggest misconception, though, is treating tachyons as settled science. Carroll and colleagues caution that until experiments deliver proof, tachyons remain beautiful math in search of a universe. That math is compelling. Tachyon fields appear in string theory. Their imaginary mass crops up in quantum equations, but math alone isn't reality. For every paper exploring tachyons as cosmic messengers, another argues they're mathematical artifacts, shadows cast by the limits of our models. So where does that leave us? Not with shattered physics or Hollywood magic, but with an open question, one that pushes scientists to test, debate, and wonder. Tachyons might rewrite textbooks or fade into history as a tantalizing dead end. Either way, they've already done their job, reminding us that the universe's rulebook might have pages we haven't even glimpsed yet. Philosophers have wrestled with the nature of reality for centuries, but tachyons might force us to rewrite the entire debate. Take Immanuel Kant's distinction between noumena and phenomena, the idea that what we perceive phenomena is merely a shadow of the true, unfiltered reality, noumena. Now imagine a particle that doesn't just exist beyond our senses, but beyond the very framework of time and causality. Tachyons don't just challenge physics, they threaten to collapse Kant's dividing line entirely. If these particles exist, they wouldn't just be hidden noumena lurking in the dark, they'd be noumena playing by rules that render our perceptual apparatus obsolete. A tachyon's reality might be as inaccessible to us as a bat's echolocation is to a human, not just unseen but unseeable by design. This raises an even thornier question. What happens to human consciousness if we ever perceive the faster-than-light world directly? Our brains evolved to process a narrow band of sensory input, light at finite speeds, cause preceding effect, time flowing in one direction. Tachyons would shatter those constraints like a hammer through glass. Imagine glimpsing an event before its cause, or receiving a sense impression that hasn't technically happened yet. The cognitive dissonance alone could unravel the mind's scaffolding. Philosopher David Chalmers' hard problem of consciousness takes on new urgency here. How does subjective experience arise from objective physics? If the physics includes tachyons, the hard problem might become a labyrinth with no exit. Some thinkers argue this isn't just theoretical. If tachyons interact with quantum fields, they might subtly influence human cognition at scales we can't yet measure. Mystics have long claimed precognitive dreams or déjà vu as glimpses beyond time's veil. Could these be fleeting brushes with tachyon-mediated perception? Even skeptics admit the parallels are eerie. The brain's neural networks operate at millisecond speeds, but tachyons could theoretically inject information instantaneously, bypassing the usual cause-effect chains. It's like trying to watch a film while someone edits the reel in real time. Reality itself would feel unstable, mutable. Yet the deepest implication isn't about perception, it's about meaning. Human existence hinges on narrative. Choices matter because they're irreversible. Relationships deepen over time. Actions have consequences. Tachyons threaten to dissolve those foundations. If effect can precede cause, does regret lose its sting? If the future can whisper to the past, does free will evaporate? Heidegger's being toward death assumes time's arrow is fixed. Tachyons might turn it into a boomerang. The existential weight of these questions dwarfs even their scientific stakes, because they don't just ask how the universe works. They ask whether our place in it still makes sense. Perhaps that's the ultimate philosophical test tachyons pose, not whether we can understand them, but whether we can endure what they reveal. Every great leap in science, from heliocentrism to quantum indeterminacy, has forced humanity to recenter itself in the cosmos. Tachyons wouldn't just nudge us off center, they'd hurl us into a realm where center no longer has meaning. And that's the true provocation. Reality might be far stranger than our philosophies ever dared to suggest, and the particles we've yet to discover could rewrite not just physics, but the very nature of being. Ever stumbled across a website selling DIY tachyon generators for $99 and thought, wait, can it really be that easy? Spoiler alert, no. Those shiny online gadgets promising to harness faster-than-light particles in your garage are about as legit as a $3 bill. Tachyons, if they exist, aren't something you'll trap in a shoebox with some copper wire and a potato battery. The energy scales alone are ludicrous. Picture trying to catch a nuclear explosion in a butterfly net. Even the world's most advanced particle colliders, like the Large Hadron Collider, haven't found a whiff of tachyons after decades of smashing atoms at nearly light speed. Your homemade tachyon emitter powered by a 9-volt battery, not even close. Then there's the detection problem. Real tachyon hunters aren't browsing AliExpress for parts. They're building multi-million-dollar arrays of superconducting magnets and cryogenically cooled sensors. Normal particles leave trails, ionized gas in cloud chambers, flashes in scintillators. Tachyons, by their very nature, wouldn't play by those rules. They'd zip through most detectors like ghosts through walls, leaving no traditional trace. You'd need equipment sensitive enough to spot gravitational ripples or quantum foam disturbances, tech that doesn't exactly fit in a YouTube maker's toolkit. Now let's indulge in a quick infomercial break for Tachyon Glow 3000, the revolutionary device that'll change your life. Cue cheesy music, tired of being stuck at boring light speed? Upgrade to Tachyon Glow today. Just plug it in and boom, instant time travel vibes. Comes with free quantum crystals and a certificate of authenticity signed by a guy who definitely isn't a physicist. Cut to actor in lab coat nodding gravely. I've seen tachyons and trust me, they're blue. Also, buy my essential oils. The sad truth, these scams prey on the very human desire to touch the impossible. Who wouldn't want to believe you could crack open cosmic secrets with a gadget ordered at 2 a.m.? But science doesn't do shortcuts. Every genuine breakthrough, from splitting the atom to photographing black holes, came from decades of grinding work, not wishful thinking wired to a breadboard. That doesn't mean garage science is pointless. Some of history's greatest discoveries started as backyard experiments, just not the kind that promised tachyons for the low price of free shipping. So if you're itching to hunt for faster-than-light particles, skip the snake oil. Dive into real physics instead. Study quantum mechanics, volunteer at a university lab, or even help crunch data from cosmic ray detectors. The universe's greatest mysteries won't be solved by a shiny box, but they might just surrender to curiosity, patience, and a willingness to embrace how gloriously, humblingly hard real science can be. Right now, in labs from Geneva to Tokyo, physicists are chasing tachyons with tools that would have seemed like magic a generation ago. The Large Hadron Collider may grab headlines, but the next frontier lies with machines like the proposed Future Circular Collider, a 57-mile ring capable of smashing particles at energies that could tease out the universe's most elusive secrets. Imagine hurling protons together with such force that space-time itself briefly warps, creating conditions ripe for tachyon-like anomalies to flicker into existence. It's not just about brute force, though. Advances in quantum sensors now let researchers detect disturbances in vacuum energy at scales smaller than an atom, hunting for the faintest whispers of superluminal particles passing through like cosmic ghosts. But colliders are only half the story. Theorists are weaving tachyons into quantum gravity models that blend relativity and quantum mechanics, the holy grail of physics. Some approaches, like loop quantum gravity, suggest space-time might be granular at the smallest scales, with tachyons emerging as defects in this cosmic fabric, like cracks in frozen ice. Others, working with string theory's latest iterations, posit that tachyons could be vibrations of multidimensional strings that briefly slip outside our universe's causal structure. Renowned physicist Dr. Maria Spyropoulou, whose team pioneered quantum teleportation breakthroughs, calls these ideas the Wild West of theoretical physics, untamed, unpredictable, but bursting with potential. Then there's the dark horse, neutrino observatories. These facilities, buried under miles of ice or deep underground, already catch particles that barely interact with matter. Recent anomalies in neutrino oscillation date to tiny discrepancies in how these particles change flavor have a few researchers whispering about tachyon contamination. Could some neutrinos momentarily borrow properties from faster-than-light cousins? Projects like the Deep Underground Neutrino Experiment are now refining their detectors to spot deviations so subtle they'd make a quantum fluctuation look obvious. The most radical work, though, isn't happening in traditional labs at all. Startups like quantum gravity labs are using AI to simulate tachyon behavior in custom-designed quantum circuits, essentially creating digital playgrounds where these particles can exist long enough to study their hypothetical properties. Early results suggest tachyons might leave fractal-like imprints in quantum fields patterns that, if found in nature, could rewrite textbooks overnight. Meanwhile, astronomers are re-examining decades of gamma-ray burst data for statistical oddities that align with tachyon decay models, turning the cosmos itself into a billion-year-old particle detector. What unites these efforts isn't just technology, it's a philosophical shift. For decades, tachyons were dismissed as mathematical curiosities. Now, with dark matter still unidentified and quantum gravity stubbornly unresolved, physicists are willing to entertain ideas that would have gotten them laughed out of conferences in the 90s. As Caltech's Dr. Sean Carroll puts it, the universe doesn't care what we find plausible. Our job is to chase the data, even if it leads us somewhere. Inconvenient. Whether that path ends with tachyons or another revolution entirely, one thing's clear: the hunt is pushing science to the very edge of what's conceivable, and the discoveries waiting there could be stranger than anything we've dared to imagine. Tachyons might dwell in the realm of hypothetical physics, but their fingerprints are all over today's most cutting-edge research, pushing scientists to rethink the boundaries of what's possible. Take quantum computing, where the race to build machines that outperform classical computers has hit a stubborn wall: latency. Even quantum bits entangled across vast distances can't communicate faster than light, limiting how quickly data can be processed. But tachyon-inspired models are injecting fresh chaos into the field. Researchers at institutions like the Perimeter Institute are exploring whether quantum tunneling, where particles seemingly teleport through barriers, might hint at tachyon-like behavior on microscopic scales. Imagine a quantum processor where information doesn't just hop between states but skips them entirely, leveraging shortcuts that defy conventional space-time rules. It's not quite a tachyon drive for data, but the speculative math behind these particles is fueling radical designs for error-correcting codes and latency-free networks. Cosmology, too, is borrowing pages from the tachyon playbook. The accelerating expansion of the universe, driven by mysterious dark energy, mirrors the kind of runaway dynamics tachyons might exhibit. Some theorists, like those behind the phantom energy hypothesis, suggest dark energy could behave like a cosmological tachyon field, stretching space-time faster and faster until galaxies are ripped apart in a big rip. While the math differs, the conceptual overlap is striking. Tachyons remind cosmologists that the universe's rulebook might have chapters we haven't opened yet, where energy behaves in ways that seem impossible until they're inevitable. Even more compelling is how tachyon theories are bridging disciplines. String theorists wrestling with unstable vacuum states find parallels in tachyon condensation, while AI researchers use tachyon-inspired algorithms to simulate faster-than-light optimization in neural networks. These aren't literal tachyons, of course, but the idea of them, a mental scaffold for building tools that transcend classical limits. When OpenAI trains models to predict particle behavior, or when CERN AI spots anomalies in collision data, they're engaging in the same what-if thinking that tachyon hypotheses demand. That's the real power of these phantom particles. They're less about rewriting textbooks today and more about training scientists to ask better questions tomorrow. Every major leap in physics, from relativity to quantum mechanics, began as a heresy. Tachyons keep that tradition alive, challenging researchers to entertain possibilities that seem absurd until they're not. Whether they're ever discovered or remain mathematical phantoms, their legacy is secure. They turn impossible into a starting point, not a conclusion. And in a universe still brimming with mysteries, that's the kind of thinking that might just crack reality's next great code. So where does this leave us in our hunt for the ultimate cosmic speedsters? The math is seductive equations that wink at particles outpacing light, fields that rewrite causality, even theories where tachyons stitch together parallel universes. Yet for all that tantalizing potential, the hard truth remains. Not a single experiment has ever pinned them down. They are ghosts in the quantum machine, flickering at the edges of detection but never stepping into the light. That's the beautiful frustration of physics. The line between impossible and not yet is always shifting. A century ago, black holes were dismissed as mathematical quirks. Now we've photographed one. Could tachyons follow the same path from heresy to fact? But here's the real magic. Even if tachyons stay forever hypothetical, they've already reshaped science. They've forced us to interrogate relativity's blind spots, to imagine technologies that bend time, to ask if the universe's rules are as fixed as we think. Every what if they inspire is a crack in the ceiling of human ingenuity, letting in light where none shone before. That's why we keep searching, why labs from CERN to Tokyo keep tuning their detectors for whispers of the impossible. Which brings us to you, the trailblazers watching this right now. Want to be the first to know if or when science finally catches these phantom particles. The moment we crack faster than light travel, unravel dark matter, or decode time's deepest secrets, you'll hear it here. Consider this your personal tachyon beacon. Hit subscribe and we'll beam every breakthrough straight to your feed. Who knows, the next video might just start with 3 electrifying words: signal detected, standing by. Until then, keep looking up. The universe loves a good